if you removed the atmosphere of Venus and replaced it with lead, the pressure at the surface would be roughly equivalent. That observation belongs to planetary scientist David Grinspoon, one of the few researchers who has spent decades arguing we should go back. He says it with the kind of calm that only comes from having thought about a thing long enough to stop being surprised by it. Those are not my words. But here is what those words mean, translated from the language of science into the language of your body. You would be crushed simultaneously from every direction by a force 92 times greater than anything you have ever stood in. Not 92 times greater than a storm. 92 times greater than the entire weight of Earth's atmosphere pressing down on you right now. The atmosphere you are breathing, the one you have never once had to think about. You would not feel it happen. There would be no sensation of being crushed, because crushing implies a process, a duration. This would be instantaneous structural failure. You would simply stop being a person and become briefly a warm geometry. And that is not even the most dangerous thing about Venus. For most of human history, Venus was hope. It was the bright one, the morning star. Ancient cultures built calendars around it. The Mayans tracked its 584-day synodic cycle with an accuracy that shames early European astronomy. The Greeks called it Phosphorus when it rose before the sun, and Hesperus when it set after. They thought it was two different objects, which tells you something about how much they wanted it to be two different things, two chances at a neighbor in the sky. Even into the 20th century, Venus wore the costume of a twin, same size as Earth, within 300 kilometers. Same mass, within 2%. Same distance from the sun, give or take 40 million kilometers, which in cosmic terms is a rounding error. Early astronomers who pointed telescopes at it saw only clouds, and clouds on Earth mean water, and water means life. And life means we are not alone in a universe that increasingly seems indifferent to our presence. Science fiction writers of the 1930s and 1940s built entire civilizations there. Swamps, dinosaurs, warm, fecund, slightly damp versions of the Cretaceous, waiting for us just next door. Ray Bradbury wrote Venus as rain. Endless, beautiful, suffocating rain that drove colonists mad with its constancy. Even his nightmare Venus was alive. And then the data came back. The first signal arrived on December 14th, 1962. Mariner 2, the first spacecraft to successfully conduct a close flyby of another planet, swept past Venus at a distance of 34,773 kilometers and returned numbers that took several readings to believe. Surface temperatures between 425 and 500 degrees Celsius. Not the surface of a warm swamp, the surface of a self-cleaning oven set to maximum and left running for 4 billion years. The swamps evaporated conceptually in an afternoon. But the scientists could console themselves. It was a flyby. It was remote sensing. Perhaps the instruments were calibrated wrong. Perhaps the surface was anomalous. They would need to go deeper. The Soviet Union went deeper. The Venera program, one of the most audacious and underreported engineering achievements in the history of space exploration, dispatched 18 probes toward Venus between 1961 and 1984. They were built to survive. Venera 7, launched in August 1970, was designed to withstand pressures of 180 atmospheres, twice what scientists then estimated Venus required. It was not hubris. It was Soviet engineering conservatism. Build it stronger than you think you need to, and then build it stronger than that. On December 15th, 1970, Venera 7 entered the Venusian atmosphere. It was moving at 11.5 kilometers per second. The parachute deployed, and then silence. The probe appeared to fail. Soviet engineers listened to their receivers and heard nothing useful. It was only months later, during a detailed reanalysis of the data, that scientists discovered Venera 7 had in fact reached the surface. It had survived. It had transmitted. But the parachute had partially collapsed under the aerodynamic violence of the descent, causing the probe to arrive faster and harder than planned. It had landed, or more precisely, it had struck the surface and come to rest at an angle, and for 23 minutes it had sent back temperature readings of 475 degrees Celsius and pressure readings of 90 atmospheres. 23 minutes. That is how long the most robust piece of hardware humans had ever sent to another planet's surface managed to survive Venus. 23 minutes, at an angle, broadcasting a whisper into the void before the heat erased it. But here's the part that nobody talks about. 23 minutes is actually an achievement. It means the engineers got something right. It means the planet didn't kill it instantly. Later Venera probes, better insulated, better sealed, better everything, managed between 32 and 110 minutes. The record is held by Venera 13, which landed on March 1st, 1982, and returned color photographs. Actual color photographs, the first ever taken on the surface of another planet. For 127 minutes before going silent. Look up those photographs. They are worth finding. The surface of Venus in them is orange. Not a warm sunset orange. A flat, oppressive, photochemical orange. The color of a world that has filtered out every wavelength of light you would find comforting. The rocks are flat and sharp and stacked like collapsed books. The sky at the horizon is a bruised amber. There is no movement. There is no wind visible, though the wind was there. Recorded at between 0.3 and 1 meter per second at the surface, almost gentle, the most deceptive thing about the entire planet. 127 minutes. And then the planet ate the camera. Now imagine you are the one who has to land there. You have descended through 96 kilometers of clouds. Those clouds, incidentally, are not water vapor. They are sulfuric acid. Concentrated sulfuric acid. 75 to 96% pure. Suspended in droplets between 1 and 3 micrometers across. Dense enough to reduce visibility to near zero for much of the descent. The acid doesn't reach the surface. It evaporates in the heat before it gets there. But during your descent, it is everywhere. It contacts any unprotected surface and begins converting it to sulfate compounds. It contacts your suit, if your suit is exposed, and begins the same process. The clouds of Venus are actively trying to digest you while you fall through them. You reach the lower atmosphere, below about 30 kilometers, and the chemistry changes. The temperature here is above the boiling point of lead. Pure lead, the metal, becomes a liquid at 327.5 degrees Celsius. The surface of Venus averages 465 degrees Celsius. If you landed in a region with active volcanic activity, and Venus almost certainly has active volcanic activity, though confirming it has required decades of orbital data, you could encounter temperatures higher still. There are highland regions on Venus where radar mapping suggests relatively recent lava flows. Recently, in geological terms, means within the last few million years, which means the planet is not dead. It is merely waiting. You step out, if stepping is a concept that applies to a person inside a pressure vessel barely distinguishable from a submarine, onto the surface. The pressure on your suit is 9.2 megapascals. For reference, a deep-sea diving suit rated for extreme ocean depths is designed to handle about 3 to 4 megapascals before structural concern becomes structural failure. You are in an environment 2 to 3 times more hostile than the deepest point a human has ever worn a suit into. The crushing pressure is not metaphorical. It is not hyperbole. It is a column of atmosphere extending 96 kilometers above your head, and every kilogram of it is resting on every square centimeter of your body. And this is where the data stops making sense, because here is what no one has yet solved. We do not have a material that can protect a human being on the surface of Venus for more than a few hours, and we do not know how to build one. This is not a funding problem. It is not a political will problem. It is a physics and chemistry problem that the world's best material scientists have been quietly circling for decades without a solution. Current spacecraft electronics fail above roughly 125 degrees Celsius. Venus surface temperatures are 465 degrees Celsius. That gap, 340 degrees, represents an engineering challenge with no current answer. NASA's Glenn Research Center has been working on high-temperature electronics using silicon carbide, semiconductors, capable of operating at up to 500 degrees Celsius. In 2017, they tested a circuit that survived 521 hours in a simulated Venus surface environment. That is 21 days. 21 days of electronics survival, with no human inside, with no life support, with no movement required. A crewed mission to Venus and back, using any currently conceivable propulsion system, would require a surface stay measured not in hours but in days, if not longer, simply to justify the fuel cost of the trajectory. The math does not close. The engineers run the numbers and the numbers come back wrong. Scientists have a name for this problem. They call it the Venus Hell Environment Challenge. They don't have a solution. But that's not even the most disturbing finding. In September 2020, a team of astronomers led by Jane Greaves of Cardiff University published a paper in Nature Astronomy announcing the detection of phosphine in the atmosphere of Venus. Phosphine, a molecule composed of one phosphorus atom and 3 hydrogen atoms, pH3, is produced on Earth by 2 processes: industrial manufacturing and anaerobic biological metabolism. Microorganisms that live without oxygen produce it as a metabolic byproduct in swamps, in rice paddies, in the intestines of animals. The detection was approximately 20 parts per billion in the Venusian cloud layers, at altitudes of around 50 to 60 kilometers, where the temperature is between 30 and 70 degrees Celsius, and the pressure is comparable to Earth's surface. The only place in the Venusian atmosphere where a human being could theoretically survive without being instantly killed is the only place where an anomalous biosignature has been detected. The paper set off a firestorm. Subsequent analyses disputed the quantity. Some reanalyses reduced the estimated concentration significantly, and a 2021 paper suggested the detection might be partially artifactual, a result of how the data was processed. The controversy has not been resolved. Jane Greaves and her collaborators stand by a positive detection. Other researchers remain skeptical of both the quantity and the interpretation. What nobody disputes is this: we do not have a complete abiotic chemical pathway to explain the presence of phosphine at Venus in any quantity. The chemistry of the atmosphere, with its ultraviolet bombardment and sulfuric acid chemistry, should destroy phosphine faster than any known geological process can produce it. Something is either producing it or we are missing something fundamental about Venusian atmospheric chemistry. Neither option is comfortable. Here is what you would experience in those cloud layers if you somehow reach them. The temperature is survivable. The pressure is survivable. The sulfuric acid is not without serious protection. But acid-resistant materials exist, and engineers have proposed cloud city concepts, floating habitats held aloft in the temperate zone for decades. In 2015, NASA's Systems Analysis and Concepts Directorate published a formal concept study for the High-Altitude Venus Operational Concept, HAVOC, a crewed airship mission to the Venusian cloud deck. It is not a fantasy. It is a technical document with trajectory calculations and mass budgets and vehicle configurations. And you would be floating in that airship 52 kilometers above a surface that kills everything we send to it, looking down through amber haze at a planet that is the same size as yours, the same age as yours, made of roughly the same materials as yours, and you would be wondering what happened. What turned it into this? What decision point in planetary history Earth took that Venus did not? Because that is the real horror of Venus. Not that it is alien, that it is familiar. 4 billion years ago, models suggest Venus may have had liquid water. A study published in 2019 by Michael Way of NASA's Goddard Institute for Space Studies and Anthony Del Genio, using climate simulations, found that Venus could have maintained habitable surface temperatures and liquid water oceans for as long as 3 billion years, longer than it took complex life to emerge on Earth. 3 billion years of potentially habitable conditions. 3 billion years. And then something ended it. The leading hypothesis is a runaway greenhouse effect, triggered by some combination of increased solar luminosity as the sun brightened over time and a decline in volcanic activity that disrupted the carbon silicate cycle that regulates planetary temperature. Carbon dioxide built up in the atmosphere. The planet warmed. The oceans, if they existed, began to evaporate. Water vapor is itself a greenhouse gas, so the warming accelerated. The oceans evaporated further, at some threshold, crossed, and impossible to uncross. The feedback loop became self-sustaining. The water was gone within geological moments. The carbon dioxide concentration climbed to 96% of the atmosphere. The temperature rose past any point of return. It happened slowly by human timescales, over millions of years, and then it was permanent. We are currently adding carbon dioxide to Earth's atmosphere at a rate of approximately 2.5 parts per million per year. Venus's atmosphere is 96.5% carbon dioxide. Earth's is 0.042%. The gap is vast. The mechanism, in principle, is identical. This is where the dread is supposed to give way to something larger, and it does, but not in the way you might expect. Look at the photographs again. The orange sky, the flat, crushed rocks, the landscape that extends to the horizon of a world that may have had 3 billion years to develop everything we have, and perhaps more. There is something devastating about those images that has nothing to do with survival odds or atmospheric chemistry. It is the silence in them. The utter, complete, geological silence of a place that was given every chance and did not make it. Or made it for a time and then lost the thread. Carl Sagan, who spent considerable portions of his career thinking about Venus, wrote that Venus is a cautionary tale. He meant it as a warning about our own climate. He was right about that. But there is a deeper strangeness in it, something Sagan was too scientifically careful to state plainly, but that the mathematics implies. If Venus had life, we will never know. The evidence would have been erased by the same processes that erased the oceans. The geological record has been overwritten. The surface is young, between 300 and 600 million years old, resurfaced by a global volcanic event that obliterated whatever came before. Whatever happened in those first 3 billion years is simply gone. Not undiscovered, not hidden, gone. We are not equipped to grieve for other planets. We do not have that emotional architecture, but something like grief is the appropriate response to Venus. To the understanding that a world the same size as ours, born at the same time as ours, may have had its own story, and the story ended without a reader. The Soviet Union sent 18 probes to Venus. The United States sent multiple flyby and orbital missions. The European Space Agency's Venus Express spent 8 years in orbit, from 2006 to 2014, returning atmospheric data of extraordinary richness. Japan's Akatsuki orbiter has been circling Venus since 2015, studying its atmospheric dynamics with instruments sensitive enough to detect wave patterns in the cloud deck that no one has fully explained. No human being has ever left low Earth orbit since December 14th, 1972, when Eugene Cernan stepped off the lunar surface and sealed the Apollo 17 hatch behind him. We have not gone back to the moon in over 50 years. We have not gone to Mars. We have not gone anywhere. We send our proxies, our instruments, our mathematics, our compressed ambitions squeezed into titanium shells, and they last 23 minutes, or 127 minutes, and then the planet takes them. Venus is not waiting for us. Planets do not wait. But the question it poses has been waiting since Mariner 2 returned those first impossible temperatures in 1962, and it has not been answered, and it will not be answered by anything we currently know how to build. The question is not whether we can survive Venus. We cannot. Not yet. Maybe not ever, with chemistry obeying the laws it currently obeys. The question is whether Venus survived itself. And the data, in every form we've collected it, in every wavelength we've observed it, from every altitude our instruments have reached before going silent, the data suggests the answer is no. We are looking at what happens when a planet loses the argument with its own atmosphere. We are looking at it from 95 million kilometers away, through telescopes and radar and the transmitted whispers of machines that lasted 2 hours in conditions that turned lead to liquid. We are looking at it, and we are taking notes, and we are calling it science. And the notes say, this can happen. This does happen. This happened here, next door, to a world that looked, for all its early history, like ours. The morning star is not a neighbor. It is a mirror. And we have not yet decided what we are looking for in it. Whether we are looking for what we might become, or what we might have already set in motion, or simply for proof that the universe does not require our survival in order to be magnificent, indifferent, and absolute.